Hello viewers and welcome to iTTV. How are you? I hope you've been finding your mathematics manageable and I hope you're ready to start a new lesson with me now. In this lesson, we are continuing with Chapter 1 of the Form 4 Additional Mathematics syllabus. It's the chapter on functions and we've been having a few lessons on it so far. This lesson, we're going to look at how to manage the relationship between the object and the image. Determining the domain, object, image, and range of a function. When a function fx is given with its domain, the range can be determined by sketching the graph. Take a look at this illustration. The graph of the function fx equals to 3 sine x in the domain where x is given as any value from 0 degree to 360 degrees is given as below. And you will see, viewers, the graph that shows you a typical sine pattern. However, the graph reaches up to as high as 3 and as low as -3. This will mean, therefore, that from the graph, the range of f is from -3 to 3. Also do note, viewers, as a gentle reminder, that the range should always be expressed in the form of a set, and hence you get the curly braces to indicate the set for the range of fx. Now, that was one example where we can use the graph to determine the range, and I'd like to show you a few more examples using the graphic calculator to determine the range of the function. Now, viewers, I'd like to show you an alternative way to determine the range of a function when you are given its domain. This method makes use of the graphic calculator, which you see before you. It is an alternative way, and although it is not included in the Form 4 Additional Mathematics syllabus, it might be just interesting for you to have a look. Let me switch on the graphic calculator first. And as you can see, I've already keyed in a function into the graphic calculator. If you take a closer look at the screen, you will find that the function we are discussing is 2x cubed minus 3x squared minus 36x plus 5. And this calculator is able to show you the graph of that function if I press the graph button over here. As you can see, the graph that results is a curly shape graph in the form of a cubic equation. And using methods which are not included in this lesson, it is found that this point is -2, 49, and this point is 3, -76. That is to say that the y-coordinate is 49 right up here, and the y-coordinate of the minimum point is -76 over here. So a lot depends on what the domain has been given as. If, for example, the question given to us states that the domain of the function is anywhere from -3 of x up till 6 for x as well, then the range of the function will be from its highest point to its lowest point. And therefore, we can say that the range of the function is -76 to 49. Now, let's try our hand at actually working out some examples from the functions given. In this example, sketch the graph of functions f and g, hence determine the range of the functions. In part A, the function of fx is given as the absolute value of 2x minus 8, where x is any value from 1 to 5. And for part B, gx is the function absolute value of 2 cos x minus 1, where x is any value from 0 degree to 180 degrees. Well, viewers, do take note of a few things. Firstly, we'll need to sketch the graph before we can obtain the answer for the range. Secondly, If the question contains the word hence, it's very important to take note of that, viewers, because hence always means that we have to use the answer from the earlier part of the question. And thirdly, do notice also that for each function, the domain was stated properly. Ready to begin this example with me, viewers? Well, in part A, function of f of x is given as absolute value of 2x minus 8. And since the domain is values of x from 1 to 5, we can begin by writing out a table of values which will help us to sketch the graph much more easily. Let me just take you through one or two examples so that all of us are very clear on how we obtain this table of values. Take for example, when x is equal to 1, we will find that when we replace 1 into here, we get 2 times 1, which is 2. Minus 8 produces the answer of negative 6. However, take note that we have the absolute value symbol here, so the absolute value of negative 6 is 6 itself only. And if you do it for the rest of the values of x, you will get these values to complete your table. How does that then show up on the graph? Well, if we plot the values in, we will find that for value of x equals to 1, your function is 6, giving us that point over there, followed by 2, 4, and 3, 2, and 0, 4, 0. We'll find that we can get a straight line that appears in this form. Let me just fill in the values to show you. This will be 2, 4, and 3, 2. Finally 4, 0, and followed by 5, 2. In determining the range of any function, we basically look for the lowest point of the graph and the highest point of the graph, and that will give us the interval within which the range lies. So, going to this example, you will notice that the lowest value of fx is 0, and the highest value of fx is 6 for the given domain. Therefore, we can say that the range for example part A is, remember, set notation applies to range, anywhere from 0 to 6. And that's our answer for part A. Moving along to part B now, we have a different function, which is gx equals to absolute value of 2 cos x minus 1. Again, a table of values can be very helpful, but this time you would really need your calculator to help you find the values of cosine x, where x would be taken to be these values. The more values we have, the better, because the graph will be much more smooth, but we also don't want to overdo it. So the x values that have been chosen are 0 degree, 30 degrees, 60, 90, 120, 150, and finally 180, since the domain of x is values which lie from 0 to 180. Make sure that when you use your calculator, you're on degree mode, and this can be found or confirmed by looking at your screen and making sure that you see that little D letter on your screen indicating degree mode. Having done all that and obtaining these values for 2 cos x minus 1, if your answers are negative, the absolute value will change it into positive, hence we get all these values to complete the table. And if we then plot the points onto our graph, we will be able to get the graph of gx. You will notice, viewers, that I do not have graph paper on the board with me, so this is merely a sketch, but it would be good if you had graph paper to do the sketch on proper graph paper, because then you can be a lot more accurate and your graph will be much smoother. So there we have it, viewers. I'm just going to connect the dots and we will end up with the graph for gx. As you can see, once again we start from the lowest value of y, which is the gx, and the highest value of y on this graph. We will find that the highest value is 3 and the lowest value is 0, which is on the x-axis. And so our answer for the range, viewers, would be from 0 to 3. That's our range for the function of gx equals to 2 cos x minus 1, where x lies between 0 to 180 degrees. Now viewers, I'd like to run through with you very briefly an alternative method as to how we can sketch the graphs of the absolute value functions that we were mentioning just now. This method, instead of using a table of values, involves the idea of reflection on the x-axis. Let's take a look at the first function that we were discussing just now. Now, as you know, the first absolute value function we used was y equals to absolute value of 2x minus 8. Do you know how to draw the graph of y equals to 2x minus 8 in the first place, viewers? Well, let's take a look at it together. Y equals to 2x minus 8 is a simple straight line, and a straight line is very easy to draw. As long as you can find 2 points and with the help of your ruler to connect those 2 points, you've got your straight line easily done. The 2 points that I'm referring to here would be best to be found by taking the x and the y intercepts. And a good way to show the x and y intercepts is to put them into a simple table. It's as simple as that, viewers. You place x equals to 0 and y equals to 0 respectively into the table, and with simple calculations from the function, we will be able to get the corresponding coordinates. For example, when x is equal to 0 into this equation, into this expression, we will have y equals to negative 8. And when y equals to 0, if you replace that into this function, you will get x is equal to 4. So with that, we will be able to draw a straight line that connects these 2 points together. Let's start by drawing the x-axis and the y-axis first. Beginning with my y-axis. We are now able to place these points onto the graph. When x is equal to 0, y equals to negative 8, places the point approximately at this location. And when x is 4, y is 0, that would place the point at approximately this location. Okay. Let's first of all draw the graph in a light manner first, because we are not going to use this as the final graph. However, we have to make some adjustments to it. As our domain given in the question begins from x equals to 1 and ends at x equals to 5, we need to take note of that in a short while. Now, the next thing that we want to come back to is the fact that the graph that we're actually drawing is the absolute value function graph. And as you recall, the absolute value function means that any value which is positive remains positive, but any value of the function which is negative becomes positive instead. Therefore, in the graph, any part of the line that lies below the x-axis originally had a negative y coordinate. These need to become positive y coordinates when the absolute value function is applied. Therefore, this is where the idea of reflection on the x-axis comes in, viewers. Notice that this part of the graph, which lies below the x-axis, In becoming positive value, it will get reflected above the x-axis, and hence we will get this portion of the graph flipping upwards to become a positive part of the graph instead. And that's how we will draw the final typical V-shaped graph of an absolute value function, and it would look something like this. Now, I'm at the same time applying the fact that the domain for this example was from x equals to 1, that would lie approximately here, and it ends at x equals to 5, which would lie approximately here. Hence, the V-shaped pattern that we're looking for, which appeared in the example previously when we did the table of values, would now appear here as well, beginning here and ending here. And from the table of values previously, we know that when x is equal to 1, the y-coordinate would have been equal to 6. Let me just label that over here. When x is equal to 5, previously taken from the table of values, the y-coordinate would have been 2. So here's an alternative way that we can draw the absolute value function of y equals to absolute value 2x minus 8. Secondly, the other function that we dealt with was y equals to absolute value of 2 cos x minus 1. Now, in this function of y equals to absolute value 2 cos x minus 1, if we try to apply the same method as we did just only, we might want to look at how the graph of y equals to 2 cos x minus 1 without the absolute value symbol yet would look like. At this stage, viewers, we may not have learned how to sketch the graph of y equals to 2 cos x minus 1 yet, which we will learn in due time, I'm sure. But there are gadgets these days, such as the graphing calculator, that can help us to get an idea of how the graph looks like. Anyway, let's just see how the concept of reflection on the x-axis could help us to sketch the absolute value function. Firstly, the graph of y equals to 2 cos x minus 1 looks roughly like this. And once again, viewers, I'll start off by drawing it very lightly because the actual function that we want to end up with is the absolute function. So the graph of y equals to 2 cos x minus 1 has a y-intercept of 1, and it carries this shape. It also has a minimum point at -3. And some important angles to notice or to take note of are the 0 degree, and the end of the domain at the moment is 360 degrees, with several other important angles to take note of, which are 90 degrees over here, where it cuts the x-axis, 180 degrees, where it experiences the minimum point, and finally 270 degrees, another x-intercept. But two things to take note of here at the moment, viewers. Firstly, the domain given for this particular function was x lies from 0 degrees to 180 degrees. Therefore, we will end up with sketching the graph only within that domain. And secondly, for the absolute value function, remember, we are going to use the idea of reflection on the x-axis. So any portion of the graph which is above the x-axis stays in its original position, but any portion of the graph which is below the x-axis will need to be reflected upwards. Therefore, viewers, I'm sure you can see already that from 0 degrees to 90 degrees, the graph will stay put in its original position. But from 90 degrees to 180 degrees, since it originally lies below the x-axis, we will need to reflect it upwards. Hence, the value of y-coordinate -3 will now become +3 when we reflect it upwards. Therefore, looks like I'll need to extend my y-axis a little longer to incorporate the y-coordinate of positive 3, which comes up to approximately here, as I bear that in mind. Reflecting it upwards gives us up to this point. Therefore, I've sketched in the point of y-coordinate of 3 for the absolute value function curve. So viewers, this is again just an alternative way to sketch the graphs of absolute value functions. But in the end, if you feel that you're not comfortable with this method, it's always perfectly alright to go back to the table of values method that we discussed previously. Determining the image of a function given the object and vice versa. Given the object and function f, the value of the image can be determined by substitution. For example, given that the function f of x is equal to 3x plus 1 and x is equal to negative 2, then the image would be f of negative 2. And this means, viewers, that we should substitute negative 2 in place of x in the function. That's why you see 3 times negative 2 plus 1, and that gives you the answer of negative 5. Hence, the image of x equals to negative 2 will be negative 5. Similarly, if 4 is the image of fx equals to 3x plus 1, then to find the x value, simply equate the function fx to 4. That is, 3x plus 1 equals to 4, and that can be solved algebraically by throwing the 1 to the right-hand side, producing 3x equals to 3, and hence x is equal to 1. Are we ready to try our hand now at our next example? Given the function fx is equal to 4x plus 3, find a. the images of part 1, negative 2, and part 2, 0 as the objects, and find b. the objects that correspond to the image part 1, negative 6, and part 2, 6, and finally part c. find the value of the object that maps to itself. Let's go over to the board now and work this out together. In part A, we are learning how to use the object in order to find the image, and we do this by substitution. So in part 1, x is given as the value of negative 2. That's the object. So to find the image, we'll replace negative 2 into the function f of x. Hence, we get f of negative 2. This is to indicate that we're finding the image for the object negative 2, is 4 times negative 2 plus 3, and that gives us the value of negative 5. Secondly, part 2, x is equal to 0 is the object given to us. We'll do the same thing, but this time we should be writing f of 0. That's because your x value is equal to 0. And substituting 0 into your x gives us the final answer of 3 as our image for the object 0. Moving on to part B, we're finding out the object this time from the image given. That means that we are kind of working backwards, but we can still apply the concept of substitution, except that we are substituting the given value into the function. Therefore, if fx is equal to negative 6, which is the way to write when they say that the image is negative 6, we can then say that 4x plus 3 is your fx. And when you solve this equation algebraically, you'll find that 4x is equal to negative 9, giving us x is equal to negative 9 over 4. That was the object that produced the image of negative 6. The same applies to part 2. When fx is equal to 6, we will find that we have 4x plus 3 is equal to 6, giving us 4x is equal to 6 minus 3 when you throw the 3 over to the right hand side. And so the object that would have produced the image of 6 is 3/4. Let's go to part C. The question itself is quite unusual. It says, find the object that maps to itself. What does that mean? Well, firstly, to find the object means we have to solve the x. Remember, object always refers to the x, while image refers to the f of x. So, to find the object means we're looking for the value of x that maps to itself. This would mean that even if it went through the function, the answer will come back to x itself. That's the meaning of maps to itself. Sometimes we also call this a mirror image. And therefore, what we want to say is that although x has been placed into the function, it still comes back as its own self. Hence, we can say fx is equal to x. That means we can then replace fx as 4x plus 3 and equate it back to x. Solving this will produce 3x is equal to -3, and then the value for x is equal to -1. So you will find that the value of x equals to -1 will produce back the solution of -1 itself too. That means both the object and image turn out to be the same number. To wrap up this lesson, we've basically been discussing two ways of working with functions. When we work with functions, we should be familiar with knowing how to obtain the object or the image in whichever question has been given to us. We can apply the method of sketching the graph to determine the range of the function, or we can apply the method of substitution and use algebraic methods to solve either the object or the image of the function. That's about it for this lesson this round, viewers, and I look forward to seeing you again in our next lesson. Meanwhile, happy studying, happy revising, happy learning. Goodbye from iTTV.